This tutorial is about automated analysis of myotube fusion using the Baxter algorithms. In this assay we grow muscle cells in differentiation media, and then we stain the cells for myosin heavy chain here in red, and the nuclei are marked with DAPI in blue. Then we want to analyze the amount of fusion, and that's analyzed using the fusion index, and that is the number of nuclei inside fibers divided by the total number of nuclei. In order to analyze these images, we first need to load settings for segmentation of the nuclei. So I go to Fusion, Nuclei, and load these settings. Then we go to the set segmentation parameters, and we see that we have the bandpass segmentation algorithm. The segmentation channel is just the first channel. In this case it's myosin heavy chain, so we need to change it to DAPI. We don't have any background subtraction. The minimum area is 10 pixels. We're using a watershed transform, and here are the parameters for the bandpass filtering algorithm. If you want more details about this, you can look at the tutorial about tracking in fluorescence microscopy. There I describe how the parameters can be changed to optimize the segmentation. But here we'll look at the segmentation results with the default settings, and they look pretty good in the first image. So I'll save these results for all the sequences, and then I'll look to see if they worked well in all of them. This one also looks good, and this one as well. So I'll keep these settings, and then I go to automated track to compute the segmentation. I call this tracking version nuclei, and I write a short note saying segmenting nuclei using default settings. I start the processing. Now the processing is finished. Then I'll go to fiber correction to look at the results. So here is the segmentation result. The program treats segmentation of one image as tracking of an image sequence with a single image in it. So that's why I had to go to the tracking menu. Now we load settings for the segmentation of myotubes instead. So I go to Fusion Myotubes and save and load these settings. Then we go to the set segmentation parameters to look at the segmentation results. Here the segmentation channel is still set to DAPI. It doesn't change when you load something. So we change it to myosin heavy chain, and then we segment these fibers pretty well. So I save these settings for all of the images, and then I go to automated track to generate the tracking result, or segmentation result in this case. once the processing is finished, we can look at the segmentation results again. So here we have the myotubes, and here we have the nuclei. And then we can perform the analysis by going to Analysis, Myotube Fusion Analysis GUI. And here we select the myotube tracking results with the segmentation results and the nuclei segmentation results. We also get to set an overlap threshold, and this threshold specifies when a nucleus is considered to be inside a myotube. In this case, it has to overlap with a myotube with 25% of the nucleus area. So 25% of the nucleus has to be inside the myotube area to be considered part of the myotube, inside the myotube. And I'll also check this checkbox to plot the segmentation results. Now the processing is finished. We can look at the three images here. The myotubes and the nuclei inside them are colored white, and all of the other objects, myotubes and nuclei, are colored in gray. So for example, we see this nucleus did not overlap enough with this myotube to be classified as being inside it. Here's another image. Here's the final image. So the myotube fusion index is the number of nuclei inside fibers, so the number of white nuclei divided by the total number of nuclei. And to see these myotube fusion indices, you go to the terminal window. In this case it's the command window MATLAB, but if you're running the deployed version, it's going to be a separate terminal window. And here we see that the fusion indices of the three images were around 50 or 60%, and the average fusion index is 58% or 0.58. Then there's also a pooled fusion index, and in that fusion index we've considered all of the fibers and the nuclei together as if they were in the same image. So if there are more nuclei in one image, that image will have a bigger effect on the final result.